All right, and the last thing we'll look at today is the spring coefficient. And so, a spring, within its elastic limits, that is to say, uh, before you stretch it so far that it starts like deforming permanently, a spring compresses or stretches at a rate proportional to the force it encounters. So, within those limits, like before you start actually destroying the spring, if you give it, if you apply a force to the spring, it'll deform some amount. It'll either stretch or compress depending on the direction you're applying that force. Now, if you double that force, the compression or stretch will be double what it was before. If you triple it, it'll be triple what it was before. So this relationship is described by this equation, which is a version of Hooke's law, where force is equal to K, which is a constant called the spring coefficient, times X. X is the deformation in the spring, either a stretch or a compression. Now, the spring coefficient is basically a measure of how springy the spring is. So, a spring that is very springy, that is to say, it takes a lot of force to stretch it or compress it, will have a high K. A very light spring, think about like a slinky, would have a very low K. To illustrate this concept, let's do a problem. What is the tension in a spring with a K of 55 newtons per centimeter if it is stretched by 3.5 centimeters when an object is hung on it? What is the mass of the object? All right, let's first look at the object. Let's try that spring again. So here's an object with a spring attached. Now, let's redraw this as a free body diagram. This object will have gravity acting upon it downwards. And it'll also have a tension force, that's the force, the tension in the spring, acting up on it. And those two, when it comes to rest, will be balanced. The tension force will equal the gravitational force, and this object will just hang on a stretched spring without accelerating. It'll stop moving. So let's take a look at this then. Going back to our equation, F equals Kx. Our K in this case is 55 newtons per centimeter, and our X is 3.5 centimeters. 3.5 centimeters, that's the amount of stretch in the spring. Looking at units, centimeters will cancel and we'll be left with an answer in newtons. Now, because we're looking for a force, that's completely appropriate. So this is the spring force equals 55 times 3.5, which is equal to 192.5 newtons. That's the spring force that is holding the object up. Now, because that's the spring force, that's the tension in the spring, that's acting upward, the force of gravity is equal to the negative of that, 192.5 newtons down. So the spring force, or the tension in the spring, is equal to 192.5 newtons up. The force of gravity is equal to 102.5 newtons down. Now, remembering that the force of gravity equals m times g, we can, because we have gravity, the force due to gravity, because we have g, which is 9.8 meters per second squared, we can find mass. And so mass rearranging that equation, equals Fg divided by g, which equals 192.5 kilogram meters per second squared divided by 9.8 meters per second squared. Now, looking at units, second squared will cancel over here, meters will cancel over here, and we'll be left with an answer in kilograms, which is completely appropriate since we're looking for a mass. So mass will equal that, and that works out to 19.6 kg. And of course, there are some practice problems for you to work on. From the text, page 49, questions 3.48 to 3.54. You can work on those in class this week, and we will have a quiz on the second class, the 1 hour class, on graphing motion. All right, so do be prepared for that.